Hello everyone, and welcome back. Last time we started to look at these two new quantities, work and energy, and we saw how we could use those to analyze different kinds of motion. What we found was the principle of conservation of mechanical energy at the end of class, and I'd like to start up with that at the beginning of class today, and we're going to continue looking at work and energy and actually incorporate different kinds of forces in our analysis of work and energy. The principle of conservation of mechanical energy states the total mechanical energy, remember the mechanical energy was equal to the kinetic energy plus the potential energy, of an object remains constant as the object moves, provided that the net work done by external non-conservative forces is zero. Remember, a non-conservative force would be something like a pushing force. If I push on this object, I'm doing work on the object and change the object's mechanical energy. If we allow friction to act on an object, so if something is sliding on a surface and friction does work on the object, then friction can take energy from the object and reduce the mechanical energy. As long as we have none of those non-conservative forces, pushing force, frictional force, something like that, doing work on the system, then the mechanical energy is conserved. What does that mean, conserved? Remains constant. The value that does not change. So let's take a look at an example. Let's imagine we've got a sled, like a bobsled or something like that, maybe from the Olympics, that's sliding down an icy track. Why is it important that it's an icy track? Because we want to ignore or reduce as much as possible the amount of friction that's acting on the object. We want to assume that there are no non-conservative forces acting on the object, doing work on the object. So let's imagine we have a sled with a mass of, let's say, a total of 102 kilograms at an initial height of 100 meters. 100 meters above the ground. So our ground level, that's where our height will be zero. That's where we will set our origin, our y origin, our zero height. Well, let's imagine the sled starts out from rest. Excuse me. Starts out from rest. So what's the initial potential energy? Remember, potential energy is mgh. Let me just remind us of that over here. So potential energy is energy that an object has because of its height. It's energy that is stored in the gravitational field. Remember, what does potential mean? If you say, oh, that person has a lot of potential, it means that person has the ability to become something. That person could do something in the future, so to speak. It's kind of like stored potential. I mean, I hate to use the word over again, but it's like something that's stored in that person. This has potential energy. If we put it up higher, it then has the potential to turn that energy into another kind of energy, energy of motion, which is what kinetic energy is. Kinetic energy is energy that an object has because it's moving. It's energy of motion, and that's equal to 1/2 mv squared. The sum of these then is the mechanical energy. So up at the top, the sled has got potential energy, mgh. And if we take m times g, 9.80, times h, we get 100,000 joules. Assuming that the sled starts from rest, the kinetic energy is zero. So what's the total mechanical energy? 100,000 plus zero, 100,000. The total mechanical energy is 100,000 joules. Now let's imagine the sled slides down and then comes to, let's say, a lower height of, let's say, 75 meters. So it's come a quarter of the way down. Well, the potential energy will then be mgh times 75, and it turns out that that is 75,000 joules. Where did that 25,000 joules go? it turned into kinetic. As the sled slides down, it's losing potential energy, gaining kinetic energy. The sled is speeding up. So the kinetic energy is now 25,000 joules. So that the total is what? It's 75,000 plus 25,000. It's 100,000 joules. In other words, it's the same total mechanical energy that we started with. Let's imagine that the sled slides down further and comes down to, let's say, 50 meters. What's the potential there? Well, put in mgh, we find the potential is 50,000 joules. I'm being a little sloppy with my significant figures here. I'm not writing this as 3 sig figs in the form that we usually would do that. I just want to make sure that we see very, very simply. I don't want to make things a little confusing by writing things in scientific notation. So please bear with me just writing them out like this. 50,000. What's the kinetic? Well, we are going further down. The sled is speeding up even more. The kinetic energy increases. The kinetic energy is now 50,000 joules. So that the total is still 100,000 joules. We come down a little further, down to a height of 25 meters. The potential energy is now 25,000 joules. The kinetic energy is 75,000 joules. We've lost more potential, gained more kinetic, but the total is the same. All the way down at the bottom, where the height is 0, what has happened? At this point, the potential energy is what? 0. And the kinetic is 100,000 joules. As the sled comes down the track, the potential decreases. As the height goes down, the potential, mgh, constantly decreases. That energy is turning into kinetic energy. One way of thinking about this is, let's say, for example, let's say you have some money in your pocket and you have some money in the bank. And let's imagine that you're not making any more money and you're not spending any more money. Let's imagine you go to the bank and take some money out of the bank and put it in your pocket. Or you go to the bank, take money out of your pocket and put it into your bank account. The total amount of money, the amount in the bank and the money in your pocket added together remains the same. Remember, assuming you don't spend any of it. The money in the bank is like the potential energy. It's stored. The money in your pocket, that's like the kinetic energy. It's ready to go do something. You can go do something with it. You could go spend it or something. But the total remains the same as long as you're not spending it. Now, spending it, that would be like money lost to friction, for example. Or if you had a job and made more money, that would be like doing work on an object, pushing it, you're adding energy into the system. So you can add energy to the object if you do work on it, pushing it. You can take energy out of the object if you allow friction to do work on it, something like that. Like you could add energy to you and your account if you had a job and did work, or you could lose money from you and your account if you spent it on something. Okay, but assuming for now, because we're assuming that no work is done by the non-conservative forces, the total is constant. So that would be the situation where the money in your pocket and the money in the bank added together always remains the same. So we've got this total amount of energy, the mechanical energy, and you can switch it from potential to kinetic or kinetic to potential, but the total remains the same, and that's what we see as the sled slides down the track. Again, assuming there's no friction, we've assumed a nice icy track, so nothing is lost to friction. Very, very good. So one thing to keep in mind, though, do Newton's laws apply in this situation? Yes, of course they do. There are forces acting on the cart. We could figure out the normal force, or it's possible, the normal force and the component of the weight acting down the incline. But could we easily use Newton's laws to solve this problem? To figure out how fast is the sled moving at some particular height? No, that would be very, very difficult. To do that, we would have to know the exact mathematical form of this curve and figure out the component of the weight down the incline at every single point and figure out how is it accelerating, what's the final velocity, that would be a very, very difficult problem. However, as long as we know there's no work done by non-conservative forces, as long as we know what the height is, we can figure out what the potential, what the kinetic energy are, what the kinetic potential and kinetic energies are, and we could use the kinetic energy to then figure out what's the final velocity. So, using the conservation of mechanical energy, we can easily figure out what our final velocity is, but using Newton's laws would be a very, very difficult problem. So, although we derived the conservation of mechanical energy from Newton's laws, looking at the work done by the net force, we have found something that's very, very powerful that can be used under certain circumstances where it would be very difficult to use Newton's laws. Not that Newton's laws don't apply, but it would be hard to use them to solve the problem. Very, very good. Let's take a look at another example. Here's the problem. A slingshot fires a pebble from the top of a building at a speed of 14.0 meters per second. The building is 31 meters tall. Ignoring air resistance, find the speed with which the pebble strikes the ground, and I want to solve this for 3 different situations. First, the pebble is fired horizontally right off the building. Second, the pebble is fired straight up and then just barely misses the building so that it can come down. And then the third way is the pebble is fired straight down from the side of the building, from the top, right down the side of the building, straight down to the ground. I want to solve this problem each of those ways. And I want us to use the conservation of mechanical energy. Why does it say ignoring air resistance? Why is it important that it says that? Because we don't want to have any non-conservative forces acting in the problem. Air resistance would be a non-conservative force that took energy out of the problem, took mechanical energy from the pebble, so we want to ignore that. Great, so let's start out with the horizontal problem, the pebble fired horizontally, and see what we get. The conservation of mechanical energy tells us that the initial mechanical energy equals the final mechanical energy. That's the conservation of mechanical energy. We want to find out the speed with which the pebble strikes the ground. Where is that? How are we going to find the speed? Remember, the speed is in the kinetic energy. Kinetic energy is 1/2 mv squared. If we can find the final kinetic energy, that will allow us to solve for the final speed. So that's what we're looking for. We're looking for the final kinetic energy. To find that, we need to know the initial mechanical energy, the initial potential energy, the final potential energy. We need to solve for all 3 of those. Then we can find the final kinetic energy and solve for the final speed. So that's what we're going to do. Let's look at these each in turn then. The initial mechanical energy is 1/2 mv squared. Let's solve for that. What's m? Well, we look at the problem. There is no value for the mass. We do not know what the mass is. How can we solve for the kinetic energy and then all these other things if we don't know the mass? This is a problem you might run into on a number of occasions. Now let's think about this. We know that the initial kinetic, the initial potential, the final kinetic, the final potential, they all depend on the mass. 1/2 mv initial squared, m initial, gh initial, 1/2 mv final squared, m gh final. They all depend on the mass. How can we solve the problem if we don't have the mass? Well, we know those all depend on the mass, but if we divided off the mass, it would cancel out. The bottom line is that we do not know the mass. The mass doesn't matter in the problem. If this pebble had a mass of 1 gram, we would get some final velocity. If the pebble had a mass of 2 grams, we would get the same final velocity. Just like when we were looking at the kinematic problems, we actually never knew what the mass is. The object was flying through the air. We never had to worry about what the mass was because the final answer did not depend on the mass. Well, what are we going to do in this case? We could divide off the mass and change our equations with the mass having been removed, or there's a very simple thing that we can do instead of that. And that is, if we know that the answer does not depend on the mass, why don't we just choose a value for the mass? We can put whatever mass we want in there, almost, and we'll get the same answer. So let's choose a value for our mass. Well, I'll tell you one thing we cannot choose, and that is 0. You cannot choose a 0 mass, or else everything goes to 0 and you won't be able to solve for anything. I would also suggest that you don't use a negative mass, because adding negative signs into equations can sometimes get lost if you square things or something like that. That can give you problems, or if you have to take square roots of things. What I would suggest is choose a very simple positive number. How about 1? And let's just keep it in SI units. Let's let our mass equal 1 kilogram. That is an awfully big pebble and not something I would suggest that you shoot off the top of a tall building. But if it really doesn't matter, the mass doesn't matter, let's just stick in a nice easy number to use, even though it's relatively physically unrealistic for the size of a pebble. But that's okay. It'll give us the same answer. Excellent. Let's proceed using a mass of 1 kilogram and see what we get.